I am Vasilios Dimakopoulos, the Dean of the School of Engineering here in the University of Ioannina. Okay, I'm very happy to welcome all of you to the third talk in our spring lecture series. Today's lecture will be given by a truly distinguished speaker, Professor George Malliaras of the University of Cambridge. I will let Apostolos Avgeropoulos, the head of the Material Science and Engineering Department, host this lecture and present our speaker.
Thank you very much, Professor Dimakopoulos. It's a great pleasure and an honor to have George Malliaras, Professor George Malliaras, as our speaker in this lecture series. And I would like to say a few words about George Malliaras, who is one of the Greek scientists who make Greece an exceptional country which delivers scientists with unique abilities and very high impact in research and quality in publications, etc., etc. George Malliaras is the Prince Philip Professor of Technology at the University of Cambridge. He received his bachelor from the Aristotle University of Thessaloniki from the physics department, and also a PhD from the University of Groningen, Netherlands, and did a postdoc at IBM Almaden Research Center at the United States. Before joining Cambridge in the United Kingdom, he was a faculty member at Cornell University in the United States at the Department of Material Science and Engineering, where he also served as a director of the Cornell Nanoscale Facility and at the School of Mines in France. His research has been recognized with many awards from the New York Academy of Sciences, the United States National Science Foundation, DuPont, and also he has received an honorary doctorate from the University of Linköping in Sweden. He is a fellow of the Material Research Society and of the Royal Society of Chemistry and serves as deputy editor of Science Advances. And we should also mention his bibliometric data. He has citations well above 32,000, and his H index is 97 for the time being. In the talk, Electronics of the Brain, he will discuss some things which are related with bioorganic electronic materials. And based on the abstract from his talk, what is being mentioned is that one of the most important scientific and technological frontiers of our time is the interfacing of electronics with the human brain. This endeavor promises to help understand how the brain works and deliver new tools for diagnosis and treatment of pathologies, including epilepsy and Parkinson's disease. Current solutions, however, are limited by the materials that are brought in contact with the tissue and transduce signals across the biotic and abiotic interface. Recent advances in electronics have made available materials with a unique combination of attractive properties, including mechanical flexibility, mixed ionic electronic conduction, enhanced biocompatibility, and capability for drug delivery. Professor Malliaras will present examples of novel devices for recording and simulation of neurons and show that organic electronic materials offer tremendous opportunities to study the brain and treat its pathologies. Professor Malliaras, George, the floor, as we would say in other circumstances, is yours.
Apostole, thank you very much for the kind invitation and the exceedingly kind introduction. It's a pleasure to be with you, albeit virtually.
Thank you for accepting.
A pleasure. And I will definitely come visit in person as soon as all the restrictions are over. I have very fond memories of Ioannina and good friends and excellent hospitality. I look forward to a visit. So it's really a pleasure and a privilege to be talking to you today. Let me first launch the slides and make sure you are seeing the right display here. 1 second. So can you see the full screen presentation?
Yes, it's fine. It's absolutely fine. Yes.
Great. I hope you can also see my cursor.
Yes, we do. Yes, we do.
Wonderful. So again, thank you. It's an honor and a privilege to be with you. We'll talk about electronics on the brain, why we want to do this, how we go about doing it, and what the future in this field holds. Let me start with the motivation. And the motivation for this work arises from the fact that neurological disorders are creating a major societal problem. They are currently the leading cause of disability worldwide. Over 276 million years are lost to stroke, migraines, dementias, epilepsies, injuries of the brain and the peripheral nervous system, and other neurological disorders. So this represents something that should be on everybody's radar as a problem to be solved. Unfortunately, the solution is not going to come from the pharma industry. They're exceptionally capable. They're saving the world from COVID with the vaccines they have developed in record time. But when it comes to new drugs for treating neurological disorders, the news is not very good. There is this trend that it's called Irum's law that shows that drug discovery is becoming slower and more expensive with time. Irum is Morse spelled backwards. Moore's law in electronics describe an accelerating trend where every year when you buy a new electronic device, it's more capable and cheaper per processing power than the one the year before. Unfortunately, in pharma, the trend is the reverse one, which doesn't bode well for pharmacological treatments of neurological disorders. However, there is good news on the horizon, and it comes from electronics. There is a new field, if you wish, that is called bioelectronic medicine, which really is a game-changing technology. This example that I show here is called deep brain stimulation, and it involves implanting electrodes deep in the brain of a patient, as shown in this cartoon here, in a structure that's called the subthalamic nucleus. And through stimulation with electrical current, you can ameliorate the symptoms of motor neuron disorders, of disorders such as dystonia, Parkinson's disease, tremor, epilepsy, where it has been shown to decrease the frequency and severity of seizures. And it has been expanded, this deep brain stimulation, as a treatment to neuropsychiatric disorders, including obsessive compulsive disorder, depression. Even obesity is believed to be treatable with this therapy, with this treatment. So the video here shows a patient who has been implanted. He has dystonia, and with a flick of a switch, the stimulator is turned on, and he goes from not being able to hold a glass of water to being able to function quite normally. Let me show the glass of water here. Yeah, so quite dramatic effects. The field goes arguably back to the first experiments of Luigi Galvani back in the 18th century, where he used electricity to make the detached legs of a frog twitch. This is a now famous experiment. And 200 years later, there were already medical treatments. This is a pacemaker in circa 57, where the batteries and electronics were external. The year after that, it was the first fully implantable pacemaker. And today, you have devices that have been miniaturized to the point where they're inserted in the heart using an outpatient procedure, and they're leadless. They're very small. They can just be placed in the heart, and the patient is out of the hospital an hour later. So tremendous progress. There are many more treatments that followed. So again, late 50s, 60s, we had cardiac pacemakers for treating arrhythmias of the heart. This is a technology that today gets implanted to the tune of 600,000 patients per year. Then a decade later, late 60s, early 70s, cochlear implants for restoring hearing in deaf patients were developed. This is through electrical stimulation in the inner ear. Then spinal cord stimulations for patients with chronic pain were developed. Then the vagus nerve, which is indicated here, became a target for stimulation. This is part of the peripheral nervous system. And early studies focused on stimulating it to treat epilepsy. Then other stimulators of peripheral nerves became important, such as for bladder control. Then the brain became the target for investigations in early 2000s with deep brain stimulation for Parkinson's, for neuropsychiatric disorders. Then some other prosthesis devices for restoring vision, for sleep apnea, and lately a trend that is called electroceuticals involve stimulating the peripheral nerve to treat disorders that go beyond the spectrum of neurological ones, such as autoimmune diseases, Crohn's syndrome, Crohn's disease, things such as diabetes are all believed to be treatable with electrical stimulation. Very exciting times. This is from a couple of years ago when a major pharmaceutical, GlaxoSmithKline, teamed up with Google's parent company called Alphabet to join what is called Galvani Bioelectronics, that envisions a future where disease is treated with electrical stimulation as opposed to drugs. And since then, Elon Musk, the founder of Tesla and SpaceX, Mark Zuckerberg, the founder of Facebook, have all launched ventures in this area of bioelectronics. So very exciting, captures the imagination, and often captures the imagination for wrong reasons. If you look in a Hollywood movie, typically the man with bioelectronic tentacles is the evil villain in the movie that seeks to destroy the world as we know it. While in reality, bioelectronics is more like illustrated here. This is a boy that hears for the first time thanks to a cochlear implant. This is a device that's implanted in the inner ear. And then there is an outer part that picks up sound, translates it to electrical activity. And then an antenna beams that information to the implant inside the inner ear that stimulates and gives the sensation of hearing. And look at the wonder in the eyes of this boy as he hears for the first time. So an incredible technology. It raises ethical issues. I don't know how many of you have seen this movie, Young Frankenstein. This is the quintessential mad scientist who's trying to reanimate a dead corpse, to galvanize, as it's called, a dead corpse. And this is really capturing reality at the time after Galvani's discovery. There were really people doing crazy things. And the field suffered a major setback. It was considered to be illegal for several years to engage in any corpse reanimation. Fast forward 200 years, there were implantable pacemakers, a life-saving technology. And today you have a device which is called an implantable cardioverter defibrillator that monitors the heart. This is placed in at-risk patients and monitors the heart. And if the heart stops beating and the patient drops to the floor, this device will autonomously reanimate and restart the heart. It will defibrillate, apply a high current pulse to the heart to get it beating again. So again, life-saving technology that became a result of engaging with society. If there is one message that I want to pass from this slide, is that a scientist alone in a dark lab doing crazy research is not acceptable, is the road to causing damage to the research, while engaging with society leads to technologies that are life-saving. So with that as an introduction, let me take now a critical look at this exciting technology. Sounds almost too good to be true, right? You implant a device, you flick a switch, and then symptoms of neurological disorders go away. What's the catch? Why don't we see this deployed to patients at scale? There are some formidable limitations in this field. First and foremost is that we do not understand how the brain works. It's a very complex machine that consists of over 80 billion neurons that are connected with, each one of those is connected with 1,000 more neurons. So the connectivity is extraordinary. The numbers are astronomical. And just it's a very difficult machine to comprehend. We do understand a lot about its components, about the neurons and the way they compile information and transmit this information to other neurons. This takes place by a so-called action potential that travels down a wire that is called the axon of the neuron. And then when it arrives at the synapse, where it connects to the next neuron, it releases neurotransmitters that then either excite or inhibit the postsynaptic neuron. So these are things that we understand in a quantitative fashion, but how we go from these cellular mechanisms to microscopic behavior is something that we do not understand. In the clinic, neurologists will place electrodes either on the scalp or on the surface of the brain, or implant them into the brain and try to record electrical activity that arises from a neuronal firing and correlate it with behavior. But it's early days and there is a big gap to be filled. What we also do not understand is the reverse problem, which is the mechanism of neuromodulation. Why, if we stimulate the brain in a particular location, why do we alter behavior and stop, for example, tremor? These are all big questions that will take several years to resolve. And they come hand in hand with technological limitations. The signals that we record in the brain are very small and they're diverse. They arise from anything from small ionic currents, metal ions such as sodium, potassium, chlorine ions, to larger molecules, neurotransmitters, to even components of cells being exchanged in signaling. The environment is hostile for electronics. When you stick an electrode into the brain, it's bad for both the brain and the electrode. It's a highly corrosive environment and can damage the electrode. Finally, bioelectronics, as it's practiced today, it's highly invasive. It often means placing electrodes into the neural system. And often multiple surgeries are required in order to replace the batteries of the stimulator, to change the position of the electrode, or to replace a broken lead. So it's good to be a technologist in this field. It's a field that is limited by technology. Technology is needed to help understand how the brain works and to enable this field to flourish and medical technologies to reach patients at scale. So that's a fairly long introduction, but I try to engage with people who are not necessarily experts in the field. And now I'm going to show you 3 different technologies that we're considering. One is already in the clinic, and this goes under the umbrella of teaching electronics to communicate with biology, or teaching them a foreign language. And I will explain why I'm saying this. The second example is still in development in the lab. And the road to the clinic here is quite long, but it's a new way to get drugs into the brain if you need them. And the third example is something that started quite recently in the lab, is implants that change shape, but has progressed quite quickly and should be moving to the clinic in the not so distant future. So let me start by framing research in bioelectronics in a slightly different fashion. What we're trying to do is to interface living systems with microelectronics, or as I like to call it, nature's crowning achievement with humankind's most evolved technology. And we want to do this in order to get information from biology to electronics to diagnose disease, and in the vice versa, to actuate biological process using electronics in order to deliver treatments. Now, there are some formidable issues that we face when we try to do this. There are differences in properties. For example, in mechanical properties, you have soft tissues here, especially the brain, while electronics in their traditional form are mechanically hard. They're made out of mechanically stiff materials with a high Young's modulus. The communication between components in the biological world is very complex, takes place by exchanging ionic fluxes, larger macromolecules, components of cells, while here in electronics, the communication of these two components takes place by exchanging an electron or a whole flux, something that we understand in a quantitative fashion. Biological systems are dynamic. This little fellow will double in size and his brain chemistry will change during his life, while electronics remains rather static in the form factor in which it has been fabricated. So the lesson here is that we need to make electronics that are similar to biology, that are soft, they can speak the language of complex signals, and they're dynamic. Over the past decade, there has been tremendous progress in addressing the mechanical properties mismatch. And we now have electronics that are very thin, very flexible, and even stretchable. So they can be placed on the body or inside the body without causing significant mechanical damage. When they're placed in the brain, they obviously do penetrate, but this can be minimized. So in a sense, the mechanical properties mismatch has been addressed. And there is a lot of research today trying to address the communications gap. So to teach electronics the language of more complex signals. So I will show you two examples of that. The first one comes from the case of epilepsy, where it's a condition that affects a large fraction of the world population. Most of the times, it is not a big deal. It gets treated with pharmaceuticals. However, in some cases, patients are drug resistant, and actually quite large fraction of patients are drug resistant. And when there is drug resistance and epilepsy is severe enough to dominate a patient's life, then resective surgery becomes the next treatment option. So this means the patient is admitted to the hospital. Electrodes are implanted in the brain to localize the epileptogenic zone, to find the part of the brain that gives rise to these intense seizures. And then that part can be resected, removed, and the patient is no longer having seizures. So this is a treatment option that is available to patients with severe forms of epilepsy that are drug resistant. The challenges here are to improve the performance of electrodes so you can localize these seizures these epileptogenic zones more accurately. The way this localization is performed is by means of stereotaxic surgery, where electrodes such as this one are implanted in different parts of the brain. The electrodes are shown here. The electrodes themselves are a couple of millimeters in length. And as a result, they provide information which is in the spatial scale of several millimeters. And there is need to do better. Now, if you turn this around and view it as an electrical interfacing problem, if you have an electronic material, say silicon, which is the king of electronic materials, it has electronic carriers in it, electrons and holes. And what you want to do is to couple those electrostatically with ions in an electrolyte. So the electrolyte here being the cerebrospinal fluid, which has roughly the consistency of seawater and has ions such as sodium, potassium that are set in motion when neurons in the brain fire. So as neurons in the brain fire, these ions move and they couple with electronic charges inside the material, who are also then set into motion. And externally, we can detect that motion. This is called the displacement current, and infer that the brain has fired. Now, as shown here, this is poor coupling because you have the ionic carriers on one side of the interface, the electronic on the other, and they're separated by an oxide or a nitride that spaces them away and decreases their interaction. So the coupling between the world of biology and the world of electronics is poor. So the electrodes that I showed you earlier are made out of platinum because platinum doesn't have an oxide. And then you can have closer coupling between ions and electrons. However, even in this case, the two charges are at opposite sides of an interface, this in the liquid phase, this in the solid phase, and their coupling has a hard limit, which is determined by the so-called double layer capacitance. Never mind the details. Now, imagine that you have a material which is like a sponge. And in this material, ions from the electrolyte can penetrate. In this case, you arrive in a situation where you have within the same material biological signals and electronic signals coexisting and coupling throughout the volume of this layer. This leads to a much stronger interaction between electronics and ionics and allows you to make state-of-the-art devices. Now, there are such materials. One example I will talk about today is called P.PSS. This is the chemical structure, but for the purpose of today's lecture, you need to consider this as a sponge type of material that is permeable to ions, and it can conduct electronic charges. This is called a mixed conductor. Now, how to design mixed conductors is something that we do not understand. It's actually a current topic of research. Here's one example. You don't need to know any chemistry to tell that these two materials are very similar. The only difference is that they have some oxygens here on this side chain. This material has them, this does not. And these oxygens here make an enormous difference in performance. This material is not penetrated by ions, excuse me. The ions will pile up on its surface, and the coupling between electronics and ionics is poor. Here, ions can penetrate into the volume, and you have much higher coupling, as seen by an increased capacitance in this material. So this is the type of work that takes place in chemistry and engineering labs to develop better materials for interfacing with the brain. And it goes a step further. If you're interested in this, it goes to translating language that has been developed for electronic materials such as silicon into materials that operate in the wet state and traditionally have been described with the language of electrochemistry. Now, as I mentioned, there is this material that we have available today. It's called P.PSS. It shows a capacitance that scales with volume. And that is a sign that ions can penetrate in the whole volume of the film and couple with electronic charges. So that means, if you put the numbers in perspective, if you have 100 and some nanometers thick film of coating of P.PSS on your electrode, you increase the coupling between ionics and electronics by 2 orders of magnitude, compared to just having a flat metal electrode. Now, that means that you can now make smaller electrodes that can measure ionic signals effectively. And this is what we did here. We made electrodes that are not millimeter in size, but they're micrometer, tens of micrometers in size, the same order of magnitude as the size of neurons in the brain, the soma of neurons. And we integrated those with flexible electrodes that can follow the curvature of the brain, conform very nicely without mechanically loading the brain. So these electrodes are shown here, conforming on the leaf of an orchid. And when you place those on the cortex of a laboratory animal, you can measure the spikes that correspond to single neuron activity. So you can measure individual neurons without penetrating into the brain. This is a new capability, again, that was enabled because of new materials that couple better electronics and ionics, and was very exciting, was a very exciting development because it allows you to measure signals at very high spatial resolution to resolve single neurons without getting into the brain. And as a result of this, it was translated to the clinic. It is used today in several hospitals in the US to map the brain of patients, epileptic patients, at the highest resolution achieved today. So this was a couple of years ago already, and it was a successful example of translation of a new material into the clinic. Since then, we've been trying to push into new territory. This is the latest version of this device that has now electrodes that are optically transparent. So you can interrogate the brain not only electrically, see the single neuron signals, but also couple high resolution microscopy, optical microscopy, and be able to visualize very small structures that are indicated here in green. This is a marker of synaptic activity of the synaptic region. So you are able now to capture the high temporal resolution of electrophysiology with exceptionally high spatial resolution that's provided by super resolution microscopy. Another example of work along this area is to use these electrodes to resolve cutaneous signals. Here you're further away from the source of activity, which is the muscle, so the resolution is poorer, but still with millimeter size electrodes, you can capture the activity of underlying muscle as this person is moving their fingers. So this type of spatial resolution, millimeter spatial resolution, can help drive better prosthesis, myoelectric prosthesis, that in the future will be very articulate. So let me switch gears. So far, I've been telling you about materials that allow you to record the brain efficiently. And as a result, they allow high spatial resolution recordings. Now we're going to talk about the opposite side of this coin, materials that allow you to trigger the brain, to stimulate the brain, in this case with biochemical signals. This is again in the context of epilepsy. As I mentioned earlier, anti-epileptic drugs is the first line of treatment. In cases where there is drug resistance and epilepsy severe, resective surgery is the second line of treatment. However, there are cases where the epileptogenic zone is localized but cannot be resected because it overlaps an area of high functionality, of executive function. And then the balance between the trade-off between gain and loss for the patient doesn't work. In these cases, we advocate implanting a probe in the brain that stimulates the epileptogenic zone with drugs. Now, here you're behind the blood-brain barrier. The brain is protected by a barrier that blocks 98% of all the drugs that we know of. So it's very hard to get drugs into the brain and achieve the effect that you want. Also, the drugs that penetrate into the brain can cause side effects in other parts of the body if administered systemically. So by effectuating local drug delivery, you can, first of all, increase dramatically the gamut of drugs that you have available, including some powerful anti-epileptic drugs that would be toxic if administered systemically. Here you are administering right where is needed, and you can also administer only when is needed, and dramatically increase the gamut of drugs that you can use and avoid toxicity. So this localized delivery concept past the blood-brain barrier comes from the case of brain cancers, where after resection of a brain tumor, there are always some cells that are left, cancer cells that are left over, and you try to kill them by local chemotherapeutic delivery. And there are different technologies developed for this. There are some wafers that biodegrade and release a dose of chemotherapy, some devices that do the same, or some catheters that are implanted in the brain, and you can inject a drug solution. Unfortunately, none of these treatments is suitable for epilepsy, where you need a chronic device. And quite frankly, they do not work well for the case of cancer either. This convection-enhanced delivery, when you use catheters, delivers mostly solvent with a little bit of drug, and you need to apply a lot of pressure to get it there. So it causes pressure-induced edemas and also suffers from reflux of the solution by the side of the catheter. So better technologies are needed here as well to drug the brain when is needed. About a bit over a decade ago now, there was a very exciting development out of Linköping University and Karolinska Institute, where they figured out a way to do dry delivery. And dry means you only deliver the drug without the solvent. This uses a material that's very similar to PEDOT-PSS that bridges two reservoirs, one reservoir where you have your drug, and it's in an ionic form, let's call it M+, and a reservoir where you want this drug to go. You apply a potential, and then through a process called electrophoresis, where the electric field that's caused by the applied potential grabs this ion and moves it along a solid material, and then lets it diffuse to the target, takes place. So this electrophoresis enables you to move just the drug ion and not the solvent, and it's particularly suitable for the brain. The Swedes demonstrated this technique and applied it to the cochlea, where they were able to release a neurotransmitter and show that you can modulate hearing by using this concept. Now, 10 years later, of course, the design has changed. This is how the device is designed for the brain. At the heart of it is what is called an ion exchange membrane, which is a plastic material, a polymer, that contains fixed negative charge. This is ionic charge that cannot move, is bound to the polymer chains. And then it's also loaded with the drug, which is shown here in cationic form, a positive ion. You have a source reservoir where your drug is located, and then target is the brain. If you apply a potential across this device, then what happens is the electric field will get the cationic drug through the membrane and inject it into the brain, while the opposite ions are blocked from exiting the brain because of the fixed anionic charge in this membrane. So this acts as a diode. It only moves positive ions from the source to the target and not negative ions in the other direction. Now, this is how the device looks in real life. This is for rodents, and it contains a shank that gets implanted into the brain. In it, there is a microfluidic channel that has a U-shaped tip here at the bottom, and it's perforated, but closed with an ion exchange membrane. So if we apply a potential between the inside of the microfluidic and the outside, which is the brain, then we can pick up ions of the drug that's inside the microfluidic channel and eject it into the brain. And then the depleted solution will just be guided out of the brain through this U-shaped microfluidic and be disposed outside the brain. So you load the drug solution, you start flowing it into the brain. Here you apply a potential, you just pick the drug ions into the brain, and the depleted solvent will just be discarded. And as a result, you avoid pressure-induced edemas, and you avoid reflux that plague convection-enhanced delivery. Moreover, you can switch the electric field on and off and affect the delivery process. You can control the delivery process. This is shown here. By applying 0.5 volt, you can increase the amount of drug. Here we're delivering GABA, which is a neurotransmitter, by orders of magnitude and achieve a therapeutic effect. So GABA is a native neurotransmitter in the brain that represents the break signal for neurons to stop firing. And it can be used as a powerful anti-epileptic. So shown here, tested in an animal model of epilepsy. Protocol A is where you kindle the seizure, and here is the seizure that manifests itself. Here the device is implanted, but it's turned off. Here, the same protocol, you kindle the seizure, it's shown here. You apply a potential now on the device as soon as the seizure manifests itself. And the seizure goes away because you're pumping GABA that calms down the neurons that are hyperexcited. The spikes that you see here correspond to an artifact. You are pulsing the delivery of GABA, and the pulses are getting picked up by the electrical recording signal. And then here is another experiment where we prophylactically start pumping GABA and then try to kindle a seizure, and the seizure just manifests itself. So this shows that you can prevent seizures from arising. If you have a marker that tells you there is a seizure about to happen, you can turn the device on and prevent that seizure. Now, this is in laboratory animals, and the road to translation to humans is long. But Chris Proctor, who was the first author in this study, has now started his own group here in Cambridge and is pushing this forward. In my own group, we are using this device now in oncology. We're making devices that will treat, hopefully one day, brain tumors. And the scenario is very different than that of epilepsy. For example, if you look at the volume that you target, is in several centimeters as opposed to very, very small millimeter size for epileptogenic zones. So in order to do that, we had to delve into the physics of these devices. We built different models. I won't bore you with the details, but the device design here is drastically different than the one that I showed you in rodents. Because again, tumors can be several centimeters in diameter. We needed to make sure that we can address such large volumes. This is in an in vitro model that shows that indeed centimeter scale delivery of drug is possible with these devices. So let me spend another 5 minutes and wrap up by showing you a final example. So far I showed you that you can use innovative materials to record the brain. You can use similar materials to stimulate the brain through electrically activated drug delivery. Now we're gonna address not the communication gap, but the dynamic versus static gap. And the idea is the following: a lot of neural surgery is quite brutal. So for example, for placing a cortical array on the brain, you need a quite large craniotomy. You need to remove the skull as it's shown here. You need to cut quite a large hole in the dura and then slide the electrode array underneath. Same thing for pain stimulation in the spinal cord. Here you have paddle electrodes that are placed on the spinal cord. They're very efficient. You have all these electrodes that you can stimulate the spinal cord with and numb the sensation of chronic pain. But to place them, you require a laminectomy, which is a significant procedure that requires quite a long hospitalization. An alternative is to use a so-called percutaneous array. These are these linear electrodes that are shown here. This can be slipped in through the small gap indicated here between the vertebrae. They do not require a laminectomy. They can be placed with a spinal tap, but unfortunately they shift around inside the body and they're not as efficient in delivering stimulation as these devices. So patients today have to choose a device that's efficient but requires brutal surgery, or a device that can be placed easily in the body but might come out of alignment and it's not as efficient. So we were very inspired by the field of soft robotics and demonstrations such as these ones, where you have a soft robot that is actuated by blowing compressed air in it. This is a pneumatically activated soft robot, and you can change the shape of it by just blowing air in it. So can we apply this to electronics? And by coupling microfluidics with flexible electronics, you can achieve actuation motions such as rolling in an axial direction or in a lateral fashion as shown here. These devices allow you now to make electrodes that are paddle-like electrodes that would require a laminectomy normally to be placed. But these electrodes can be rolled up to have the same shape as a percutaneous electrode that can be implanted in the body using a spinal tap. And then through pneumatic actuation, it will open up and become a paddle. So you decrease quite dramatically the impact of neural surgery. You can place those with a spinal tap, as shown here. These are results in human cadavers that maintain, obviously, the anatomy. And through a spinal tap, you can put this electrode into the body. These are two markers, X-ray markers, and then actuate it to become a paddle, as shown here. Very exciting because it decreases hospitalization time and fits the patient with a technology that really works. We're also trying this on the brain to deploy ECOGs, cortical arrays, that are as big as 2 centimeters in width through a small hole as opposed to a craniotomy. So let me conclude. I hope I conveyed my excitement for implantable electronics. I believe they hold a considerable promise for understanding the brain and addressing its pathologies. We talked about mixed conductors that enable good coupling between neuron signals from neurons in the brain and electronics. This is a technology that's already in the clinic. We talked about electrophoretic delivery that is dry. It doesn't deliver the solvent, only the drug, and as a result is suitable for applications in the brain. We showed that it can be used to control seizures in an animal model. And this will eventually, hopefully, make it to the clinic, but it's a long way. And then I talked about microfluidics that allow implants to change shape and deploy inside the body, and be placed there through minimally invasive procedures. This will hopefully go to animal patients in a year or so, and then hopefully to the clinic not so long after that, to human patients not so long after that. So with that, let me thank my group. The group is co-led by a clinician, has a very strong translational effort, collaborations within Cambridge, outside Cambridge, funding agencies. And again, thank you very much for having me today. It's a great pleasure.
Professor Malliaras, thank you very much for this stimulating, amazing, exciting talk. You gave us a lot to think about, and you know that this actually is being documented via the YouTube channel, and so I can send this YouTube channel afterwards in order to see your talk.
Thank you.
And furthermore, we have questions through the chat form of YouTube in order to let you have some questions. The talk was absolutely amazing. Congratulations on this extremely interesting work that we are doing with a high impact, I think, on medicine. And so I have two questions before I can answer some questions from the live chat. My first question is, how easy is it to actually get the material accepted for commercialization after all the research has been done, taking into account that we have worked in two different environments, one in the United States and one in Europe. So which one do you think it's faster?
So to get the material past the regulatory agencies, being the FDA in the US or the European authorities, is not dissimilar. The process is fairly similar. The timescales are a bit accelerated in the US, but you need to demonstrate safety and efficacy of your device. It's not the material itself that gets the okay from the regulator, is the device. Now, in the big difference, which is pertinent for us academic researchers, is being able to do a first in human demonstration. In the US, you can do this through what is called an IRB approval. So the Institutional Review Board of a hospital can weigh in on a proposal by a medical practitioner that I want to try this device on a patient with patient's consent. This is an experimental device that was built in a lab. We believe it's biocompatible. We believe it's gonna show some efficacy, but it is an experimental device. You can do that in the US. You cannot do that in Europe. You have to have a device that has been manufactured through a very rigorous standard, which is called good manufacturing practices. It costs about 30,000 euros to if you want to, well, no, maybe I'm underestimating, between 40 and 100,000 euros to hire some company to do that. And only then, only with that certificate, you could go to the hospital and ask for permission to try it in first in human. And this is not a clinical investigation. It's not a trial. just an experimental first in human demonstration.
I see.
So there is this difference, and the NeuroGrid, the device that I showed, was developed in 2011, and it was in a patient in 2015. This is exceptionally short time.
Right.
That was basically enabled by this IRB approval mechanism. In Europe, it would have taken much longer and would be much more expensive. That's the difference.
Okay. The second question I have is taken from the slide where you showed the villain in Spider-Man and the boy with the hearing implanted device. And I wanted to know how recent is this implant hearing device? Meaning that I didn't see any dates below on the slide, meaning when it was, taken, what time was it taken, etc.
So cochlear implants started in the late 60s by Australian researchers, and that led rise to Cochlea, which is today a world leader in this technology. So it's a very interesting question that you're asking, because the ethical dimensions of this work were very pronounced there. When this device was developed, the deaf community reacted against it. They basically said, this is not a device that we want. We have a very tight-knit community that has its own culture, and this device represents an affront to our culture. It's going to take members of our community into the hearing world and basically decimate our community. Now, that was the initial reaction. And it was seen as a bit of high-handed. Look, this is a bunch of scientists who developed this technology, and here it is. It wasn't done in good communication and consultation with the deaf community. Now, fast forward to today, the device is very much accepted. It is seen as a tool to access the hearing world. It can always be switched off. And it's seen as a valuable tool for hearing the fire alarm, hearing a car that is coming, as a safety device.
Right.
There are some ethical issues that still remain and are discussed in current literature. The brain has a window of development for language. So if a child is born deaf and doesn't get a cochlear implant early on, after a certain window, they will not be able to develop this ability to hear language. So today, these devices are fitted with the consent of parents, early stage, a very, very young age, before this window closes. What happens when the patients when the parents do not consent? That's still a question that's being debated.
I see. Thank you very much. And also, now let's go down to some questions from the audience. We had a really good, strong audience, almost 125, 130 people. So now, one question they're asking is, you said in your lab, you are working on bioelectronics for tumors and epilepsy. And they're asking what type of tumors, since there are you are working on, since there are two different ways to approach them, and
Yes.
if it's possible, and it's within your things that you may say, because what should I point out here is that of course you have a lot of things which are already patented or are going to be patented, and maybe you cannot actually release them for the time being.
Yeah, no. I can talk about this. So we're looking into glioblastoma, which is a particular hard to treat tumor. When it gets diagnosed, typically the life expectancy is about a year. It's treated currently by resection when possible, followed by radiotherapy and chemotherapy. Radiotherapy in the UK is temozolomide as the first drug. The key issue is that by the time it presents itself, by the time the patient goes to the doctor, the tumor can be quite large and it's infiltrative. It can spread its legs to different parts of the brain. So surgery is meant as a way to not to take the whole tumor out, but as a way to debulk and provide some comfort for the acute symptoms that the patient would have, release the pressure, the burden of having such a big structure in the brain. But the core of the tumor is necrotic. So all the action is at the periphery, at the interface with the healthy tissue. And that's where radiotherapy and chemotherapy come in. For chemotherapy, temozolomide can cross the blood-brain barrier, is one of the very, very few drugs that can, although it's not clear at what efficacy, how effectively it can. Ideally, you want to deliver drug locally into the brain, behind the blood-brain barrier, so that you can use something a bit more toxic than temozolomide. And also that you could change the drug cocktail. Glioblastoma is called glioblastoma multiforme. And the multiforme means there are many, many, many different cells. Every single cell in the tumor is different than its neighbor. So when you source temozolomide, you kill some cells and you evolve the rest of them. So in a sense, you need to keep chasing the remaining cells with different treatments. So a local drug delivery device has a lot of advantages in this respect.
Okay. So one other question is, how are the implantable devices being powered? Can they be powered by the human organism, or you have a smaller device which actually is related with a battery or whatever in order to give power to the implantable device?
Yeah, so it depends a bit on the context. So pacemakers and deep brain stimulators are powered by battery, which is implanted in the stimulator box, which is usually placed here under the skin in a cavity on the chest. Cochlear implants are powered from the outside. There is a part that fits behind the ear that contains the batteries there. Batteries are quite efficient today. Having said that, you still need to explant part of the device when the battery is implanted to replace batteries every 5 or so years. Some models have batteries that are implanted that are rechargeable. You can use a wand-like device and recharge them from the outside. There is a lot of research in powering these devices with biofuel cells that are implanted, but currently no practical application of that. Maybe one day in the future.
Okay. Thank you. Another question that we have is, can an oral intake drug be released in the brain?
Sorry, I didn't catch this.
Can you release in the brain an oral intake and drug? For example, through the mouth, if you take a drug, can it be released in the brain in order to relieve any tumor type
Yes.
involved with the brain?
Yes, so there are formulations of drugs that are given orally, and they can they go into the bloodstream, and then they can cross the blood-brain barrier. So this is systemic administration. Again, 98% of all the drugs that we know cannot cross the blood-brain barrier. So it's a small fraction of those drugs that can do that. When you get it in the bloodstream, they will eventually cross, including temozolomide, which is a chemotherapeutic, one of the rare ones that can cross the blood-brain barrier with significant efficiency.
A question that I have, in order to, since I see that there are a lot of students and PhD candidates, etc., watching us right now. I wanted to ask you how difficult it is when you get a bachelor in physics to be here today and know so many things about medicine.
Well, it takes time. That's what it is. Usually, look, people who come to the group to do a PhD or a postdoc are trained in a traditional discipline. And in the group, we have everything from physicists, chemists, material scientists, to engineers, electrical, mechanical, chemical, to life scientists, neuroscientists, and a couple of clinicians. All these folks are trained in their discipline, and then they evolve. They pick up, if they wish, some other knowledge from another discipline. Now, this takes time. It requires first coming up with a common language, being able to explain your discipline to someone else, and being able to understand another discipline when it's brought down to the appropriate level. So it takes time, and it takes a willingness to engage. And what it takes more than anything else is let's say the ability or the willingness to go out on a limb, to not know everything, and to kind of know a little bit, but hope to increase that more and more. For example, I started working with brain tumors rather recently, about 3 years ago. And initially I knew nothing. Now I know a bit more than nothing, but still there is a huge area that is beyond me. And it just takes time, and it will take however long it takes. Typically within 5 years, you can stand your ground at a conference and be able to field questions sounding not too much like an idiot. But you have to kind of be okay with that. You have to be okay with the fact that there are a lot of things that you will not know, and it will just take time to acquire that knowledge.
Well, thank you for saying all this, because I always, most of us tell to our students that what you learn here is a base, and then you have by yourself and with the others that you have to collaborate with. Because I really like the slide where you said that if somebody is alone in his lab and he's doing extremely nice research, this is not acceptable, because you haven't come in communication with the outside world, or you didn't collaborate with other people who maybe advance what you are doing in your lab. So as I saw, as I have seen in your last slide, you have collaborated with many people, because it's good to know that there are people there which can solve a problem that you might face, or something that you may not be able to explain. Okay, and being collaborative is a very important consent in order for us to move forward in a very competitive environment, right? You agree with that, I guess.
Yeah, absolutely.
Your slide and your talk, that's what a very strong outcome is. So we have a few more questions. If you have time to answer them.
Sure. Yeah, plenty of time.
We can take one or two more questions. Is that okay?
Sure.
Now I see that the dean is online again, Vasilis. You want to ask something, Professor Malliaras?
No, go ahead.
Okay.
Serve the audience.
Now, one question is, do you think the devices you shown can be used as translators?
Sorry?
Okay.
I didn't catch that.
Yeah, they're saying that the devices you have shown, can they be used as online translators in the brain, so you can actually speak different languages at once?
So there are devices that can decode speech in humans. So these are placed on the temporal lobe in areas that have to do with language processing. And they're used in patients with locked-in syndrome. So locked-in syndrome is when there is an injury in the spinal cord, the higher up part close to the brain. And as a result of that injury, the patient's brain works very well, but it cannot communicate with muscles. So they lose the ability to speak. This can arrive as a result of an accident, as a result of a stroke. So they cannot vocalize. In these cases, a treatment would involve placing an array in the language area, an array of electrodes over the language area, recording neural signals that correspond to the signals that the brain would send to muscles to produce the speech. But obviously that pathway is not working now, but a computer can interpret those signals and vocalize for the patient. These are called speech interfaces. There's a group in San Francisco who's pioneering this. There is also a European project in which we are involved developing this technology. So the neurogrid that I've shown is developed here in Europe for this purpose. Then once you have the volition for speech, you could generate the speech and then translate that to another language.
Another question that we have, which seems to be interesting for me, is you have shown us this device which you have looked at in mice in order to avoid any strokes, etc. And one viewer here said that, can this device, you think this device, is it possible to be applied in a pregnant woman? Meaning that during pregnancies, there might be some issues with, the diabetes or the blood sugar, etc., and also maybe a small stroke or whatever. And so, do you think that this can be applied to the pregnant woman without having any issues for the?
Yeah, it's too early to tell. It's way too early to tell. These are still experimental technologies. They haven't cleared the full safety and efficacy criteria. Sorry, one second.
Yes.
The person
We're giving you a hard time, I apologize.
No. The person who asked the question raises a very important point, is that, sorry, when technology is developed, it should be developed for all. A lot of technology is being developed for men, for white men. For example, if you look at crash test dummies,
right,
the machines that are used to test safety in cars, it's a 75 kilo male anatomy model. It wouldn't work for me, right? I'm about 100 kilos. It wouldn't work for the average woman. it wouldn't work for a kid. So a similar thing is seen in medical technology. Often the technologies are developed for having a specific white male physiology in mind. This came up recently. We're developing some large arrays of electrodes to place over the heart and measure heart activity. How do you translate this to women? It's not very clear. So in our tests, we had to develop to include women as well in order to see that whether it translates or not.
Okay. Well, Professor Malliaras, thank you very much for this stimulating talk, for accepting all these questions from our audience. Again, I want to point out that it was an honor and a pleasure to have you here in this distinguished talk series, and looking forward to seeing you in Ioannina, because we owe you a treat.
I'll be delighted to come over anytime. And you don't owe me anything. The pleasure is all mine. But I will come anyway. I enjoy Ioannina very much, and I enjoy seeing the department, seeing you and other friends and colleagues there. So thank you. Thank you very much for having me.
Thank you.
Thank you very much, Professor Malliaras.
Thank you. Bye.